Thank you, Allison, for the talk. It's a pleasure and an honor to be here. Allison sort of alluded to this, but I've never officially received any of my training from Stanford, but I think I've sort of gotten the secondhand Stanford experience, and I'll start off with, I started as an undergrad, actually, at Michigan, working in the lab of Professor Art Kuo, who many know spent his time here working with Scott Delp, doing his PhD work, and that's where I first got introduced to the world of biomechanics, human user studies. In fact, I was an undergrad in the lab when another Stanford affiliate by the name of Steve Collins was finishing up his PhD in Art Kuo's lab. And in fact, my first user study that I ever participated in was one of Steve's last user studies before he defended his dissertation. As Allison already mentioned, I did my PhD with Brent Gillespie, who of course did his PhD with Mark Kukowski. I then went on to work with Catherine Kuchenbecker, who did her PhD with Gunther Niemeyer here. And then of course, I've now started my career, academic career at Johns Hopkins University, which many of you know is where Allison started her career. And fortunately, by taking the Charm Lab from Baltimore to Palo Alto or here at Stanford, I've had the opportunity to start the Hammer Lab. And so, like I said, never officially been trained at Stanford, but I feel like I've sort of been unofficially trained through Stanford. I just wanted to take a minute and sort of acknowledge all of the students in my lab throughout the years who've done the work that I get the pleasure of talking to you about today. Being a faculty member, one of the greatest things that we talked about this at lunch is the students that come out of your lab. I also have the great fortune of having one of my first PhD students who's now here doing the Stanford Biodesign Fellowship, whose work I'll talk about towards the end of the talk here as well. So with that, I will get in because I know I got to make up a little bit of time. So we know that we use our hands and upper extremity to do a lot of dexterous manipulation tasks throughout our daily experience, right? If I were to think about it and cartoonize it, right, like we think, oftentimes we observe objects in the environment through vision. And then if you want to reach out and grab or manipulate objects in the world, we send these efferent signals from the brain out to the periphery. At the same time, we've got sensors embedded in the musculoskeletal system in the skin itself that sends all of this afferent information back to the brain and does closed loop sensory motor control. The blue trace here, the afferent signals, is what my lab really focuses in on. And I'll show an example, and I'm going to rush through it. You might have already seen this work. This is the famous Roland-Johansson experiment where you strike a match. You have the participants strike a match, right? Everybody's sort of seen this. I'm seeing nodding of heads here. Pretty simple, right? Then you anesthetize the fingers, ask them to do it again. Performance is markedly worse, right? And all you've done is sort of turn off the cutaneous receptors that are in the fingertips. Okay, just for the sake of time, I'll keep going. So how we get to telerobotics, I know I'm sort of preaching to the choir in this community here, but we know that there are certain environments where you can't directly manipulate, right? Either because they are located great distances, pose dangers to the bodies, or on different scales from the body, or we've contrived accesses in the case of minimally invasive surgery. There are also cases where the body itself changes conformation, and there we're sort of operating in our normal environment just without our healthy, intact limbs as we normally would. In both of these cases, what you need is an interface that takes your action and imparts it on the environment. These interfaces are originally called teleoperators. For the sake of time, I'm going to skip over the video of the Gert-style teleoperator, but these devices were sort of invented in the 50s and 60s by a scientist by the name of Raymond Gertz that allowed operators to handle radioactive material. What's nice about these teleoperators is that they were purely mechanical, just cables and linkages connecting the leader side of the robot to the follower. And so you had great tracking in the forward direction, sort of position mapping, but also great force reflection from the remote side back to the operator, right? Most of these teleoperators nowadays, because of electromechanical actuation schemes, are actually telerobots. In our lab, we like to think of a prosthesis as a telerobot. You're operating a distal robotic hand from more of a proximal location on the body, typically using something like EMG as the interface. And so with telerobots, right, we've gotten really good at doing one-to-one position mapping in the forward path. We measure all the interactions between the environment and the telerobot, but we don't really oftentimes pass that information back to the user. And that's what my lab focuses on, as well as Alice's and others, is how do we build these haptic interfaces to restore the sense of touch to the operator, to be able to restore this dexterous closed loop, this closed loop dexterous manipulation capabilities. In my lab, we sort of focus in on two sort of telerobotic application areas, upper limb prosthetics and minimally invasive surgery. And then we also do a lot of work in sort of fundamental haptic perception, and I'll talk about that as well. Starting with the upper limb prosthetics work, this is work that was led by my former PhD student and postdoc, Dr. Neha Thomas. And so if you were to have an amputation today in the upper extremity, there's sort of two types of devices. There's a body-powered device, which as the name implies, uses body action with the Bowden cable and the shoulder harness to open and close a prehensor, or they're myoelectric devices. Body-powered devices have inherent haptic feedback. Myoelectric devices don't. And so a lot of our work is focused on how do we restore this haptic information in the myoelectric device. It has been shown many times over that when you add haptic information into a myoelectric device, you do get improvements in task performance. We've shown that, other labs have shown that as well. We wanted to ask a sort of separate question in this study well, how good is that performance compared to what we consider the gold standard, which is the intact limb, right? So how close are we getting back to what you can do with your natural limb? And we also wanted to ask that question sort of looking at not only task performance, so like how well do you do the task, but also saying if you do the task really well, what cognitive effort does it take you to do that level of performance, right? And so this is some work that we've done in collaboration with my colleague Hassan Ayaz, who's at Drexel University, where we start looking at what we term neural efficiency. So in order to get a certain amount of task performance, you have to give up a certain amount of cognitive effort, and we're looking at the relationship between the two. Good task performance with very low cognitive effort is very neural efficient. Bad task performance with high cognitive load is very, it's not efficient at all, right? And so now we want to say, what is the trade-off between task performance and cognitive load? We ran a simple experiment here where it was a stiffness identification, or really stiffness discrimination task, where in the top right you see these little silicon blocks that had 3 different stiffnesses. We asked participants a 2 alternative force choice paradigm, squeeze one of these 2 objects, tell us which one is stiffer, right? We did this through a prosthesis that you see on the left-hand side here that allows us to work with individuals without limb difference, or non-amputee participants, or able-bodied individuals. And you can see sort of in the top left, we use this neuroimaging approach called FNIRS, functional near-infrared spectroscopy, which basically looks in the prefrontal cortex and can basically, due to neurovascular coupling, can sort of tie metabolic activity to neural activity. In the bottom left, we have a piezo-resistive force sensor that we put on the finger because, again, we're trying to compare performance between the prosthesis with feedback, prosthesis without feedback, and then the natural limb. And the bottom right just shows what the setup looks like, where you reached in with the prosthesis, you squeeze the object, we move the object out, put another object in, you squeeze, and then we ask you, of course, the question, which one was stiffer, 1 or 2, and you answer. What we found, again, I didn't mention this, but the objects that we were using were all different mixtures of silicone, so they weren't linearly spaced apart. We basically got a trimodal distribution. Depending on what object pair we asked, we got different results. So I'll focus in on the one that was the hardest of the 2, the soft medium. These 2 were stiffer, the stiffnesses were closest together. What we find is that if you look at the blue trace on the left-hand side, this is the natural limb, you're 100% accurate, right? Every time we ask you to do it with your real hand, you could identify which one, which of the 2, soft or medium, was a stiffer. We asked you to do it again with the prosthesis without haptic feedback, which is the yellow polka dot trace there. And what we find is that participants were about at the guessing rate. Remember, it's a 2 alternative force choice, so probability-wise, you have a 50-50 chance every time you guess of getting it right, and that's what we see. But when we add the haptic information back in, we see a significant improvement over the case where we don't have haptic feedback. We're also significantly worse than the natural limb, but we're sort of heading in the right direction. This result by itself is not really novel, right? Others have shown this in various other types of tasks. But now when we look at brain activity, and I'll, for the sake of argument, just focus in on that soft-medium combination again, what you're looking at here is a delta or a change in hemoglobin concentration before and after we ask you to do the comparison. So we take a baseline measure before we ask you to do the comparison, take another measurement after you've made your guess, and we look at how much that concentration has changed over time. And basically what we see is that the natural limb, again, the blue trace here, is relatively no different from 0. It doesn't take any cognitive effort to do the task. When we ask you to do it with the prosthesis without haptic feedback, it has the largest delta. Now, we didn't have haptic information, but we also didn't turn off any auditory or visual cues. So what we think is happening is participants are actually trying to make the best educated guess that they can with the limited information that they have, and that's why the cognitive effort is being driven up so much in that scenario. They aren't just like randomly guessing. But when you add the haptic feedback in, we do get a significant decrease in the cognitive effort, right? Still significantly worse than the natural limb, but significantly better than the prosthesis without haptic feedback. And when we look at the overall, what we call neural efficiency, where 0 here represents the mean neural efficiency for all of the tasks, what we see is that the natural limb has the highest neural efficiency. We would sort of expect that. The prosthesis without haptic feedback has the worst neural efficiency, and the prosthesis with haptic feedback has better than without, and is heading in the right direction of the natural limb. So we've sort of shown now that this haptic feedback, not only does it have a task performance benefit, but the task performance benefit also comes with a cognitive effort benefit as well. Okay. We've sort of been taking this experiment now and going with more complicated tasks. Remember, that one was just stiffness discrimination. We have a new task now that we tried out where we have an object, and this is sort of modeled after the sort of famous Roland Johansson grasp and lift papers, where you can sort of take the weight out of an object without knowing it and sort of see what happens. So we have a drawer here that has a weight container in it where we can take weight in and out. The device also has sort of this unique little hinge door on it, and I'll show you in a video what that does. If you squeeze too hard with the prosthesis, the door will collapse. So essentially what we've done is create a brittle object, so sort of like picking up an egg, right? Where we can actually change the mass or the weight of the egg in real time. What we've also done in this scenario is start looking at not only just direct manual volitional control with EMG, but also what happens now if you put some level of autonomy on the prosthesis as well. The type of autonomous system that we had running here was more of an imitation style learner, where if you grabbed the object, successfully picked it up and put it back down, the system remembered what was the grasping force that allowed you to be successful, so that the next time you go try and pick it up, you sort of initiate it, and then the autonomous system kicks in and picks it up for you. I shouldn't say picks it up, it grips it for you. You still have to pick it up. And so this video just sort of kind of shows you what happens here. The first time, the user is using sort of direct haptic feedback, so they're getting vibration feedback of grip force here to be able to judge what is the right grip force. And then the second time that they go do it, the autonomous controller kicks in and sort of goes directly to the right grip force, or the grip force that they used the last time that allowed them to be successful. If they aren't successful, you can go retrain it and everything like that. Okay. So we had an experiment where we basically told participants, we gave them a minute and said, how many times can you successfully pick it up and put it back down in that 1 minute? We did 7 trials of that. Basically what we found is that really the case where you have this haptic share control in the sense of the autonomous plus the volitional control with haptic feedback, we got significantly better task performance in terms of lifting the object. So you were more likely to actually lift the object when you had the haptic share control scheme going at the same time. Not significantly lower cognitive load, but sort of heading in the right direction in terms of lower cognitive load. The reason that we think it sort of ended up not being significant is because the first time that you go grab it, it's all manual. You're getting haptic feedback, and you sort of have to judge what is the right grip force. And so we think that sort of is driving it up, even though over the course of time it drops off because now the autonomous system is kicked in. But when we look at the neural efficiency, we do get a significant sort of improvement with this haptic share control over the case where we don't have haptic feedback. So sort of similar result that I showed before now, but with a more complicated task where it's not just sort of can you discriminate the stiffness of this object, but can you hit this sweet spot in grip force where if you don't grip hard enough, you don't pick it up, but if you grip too hard, you actually break it. Okay. We've then started trying this work out with actual amputee participants. We invited a participant in over the summer and had this participant try this with their clinical prosthetic limb hand, which is I think it's an iLimb Ultra hand. I don't think the sound is working, but what you will see is basically every time they try and grab it, and you can maybe hear it here, it just breaks. So by and large, with their clinical prosthesis, they were never actually able to sort of judge the right amount of grip force to be able to pick the object up. We then had this participant do the same task, same object. The only difference is we used our experimental lab prosthesis with the haptic share control algorithm running on it. And we got a sort of different result in that about 50% of the time, this participant was able to actually pick it up and put it back down. It wasn't perfect. And you'll see here at the end, after they put it back down, they still were able to like sort of break it every now and then, which you can see happen right there. But about 50% of the time, they were still able to successfully pick it back up. So we're sort of, we're starting to follow this experiment up now with more amputee participants to see what is the benefit. We've also done some other work that I don't have time to talk about today, where we looked at other types of haptic share control, not just one where it's sort of volitional or fully autonomous, where you've got volition and autonomy sort of working symbiotically together. And we get sort of interesting results there as well. The last thing I'll talk about in the prosthetic space has to do with the design of the prosthesis and the prosthetic hand itself, right? This is the B-Bionic hand, which is sort of on one of the best, let's say, commercially available hands that you can get, right? What's interesting about the B-Bionic is that its actuation scheme looks very different from that of the hand, right? Even though the form is about the same, and that's because our hands use an agonist-antagonist tendon structure to actually control limb movement. What's really nice about this agonist-antagonist structure is that not only can we control position of the limbs, but if we co-contract both sides of the muscles, we can actually control endpoint impedance. And it's been shown, actually by Allison, when she was at Hopkins, that participants modulate their impedance in real time based on the needs of the task. And so we begin to say, what if you could build a prosthesis that allows you to do this impedance control in real time? This is the first sort of prototype of such a device, where we have basically an anthropomorphic skeleton open hand that we found online that I had a student then rig up to do tendon control. Right now it's it's only all 4 fingers at the same time, open or close. And so we've got 2 tendons here serving as the flexors and the extensor tendons in the prosthesis. If you'll notice, this work kind of got published in 2020, so this happened right before the pandemic and everything got shut down, so we never got a chance to actually run the user study, but we did get a chance to make a decent video, and I'll show you what this, what this control scheme looks like. And now, I don't know if this is the best control method. This is just the one that we kind of stuck with in the interim. All right, and I stopped the video right here because when we were filming this, we didn't notice this until after we filmed it, but this interesting thing happened, right? And it sort of originates right here where this arrow is gonna point. Watch what happens when I let the video go with the hand. You see how the finger's draped over the surface of the ridge of the box? If this were a normal commercial prosthesis, that would have never happened. They would have drugged the box completely off the table, right? But this is what our limbs do sort of all the time, right? They're rigid, they're stiff whenever we need them to be, they're compliant whenever we need them to be, right? They adjust to the environment, they adjust to the task. And this is sort of our first sort of approach at seeing a limb that can actually, going towards a limb that can actually do this and adjust to the needs of the task. Okay. I'm going to start now going into the robotic minimally invasive surgery area. This is work done by my PhD student, Sergio Machaca, as well as a former visiting master student in my lab, Guido Castianiga, who's now actually doing his PhD with Catherine Kuchenbecker at the Max Planck. So we know that Da Vinci doesn't have any haptic feedback, right? So one of the areas that we started working in on, and this started in my postdoc, is looking at surgical training. What happens if you give surgeons feedback during the training phase, and does it lead to improvements in performance? So we have a very simple setup here where you can take sort of any inanimate training task, like the peg transfer task that you see here, put it on top of this platform. There's just an ATI Mini 40 sitting underneath, so we can measure all of the interaction forces between the prosthesis, that the surgical instruments impart on the task material. And then using this device that was created by Andrew Stanley and Catherine Kuchenbecker many years ago, it's just a wrist-worn device that squeezes. We can basically map the force that you produce on the task to the amount of squeezing that we produce on the wrist, right? Pretty straightforward. This is how the device, looks sort of in situ, right, when you're actually doing the task. And what we did is we invited participants in, all novice. to perform this task that you see in the top right, which is called ring roller coaster or ring walk, depending on who you ask to, or when you ask. But the idea is that you take a ring and you're moving it along the track, and you don't want to generate any force. You want to leave the ring sort of in the center of the track, not making contact. We had two groups of participants perform this task, one that had haptic feedback all the time and one that didn't, because we wanted to see, does it improve sort of the pace at which they get better at the task compared to the control group that doesn't get any haptic feedback. And we were looking both at not only their task accuracy in this case, so how well did they do the task, but also looking at, in this situation, the speed at which they did the task. So is there a speed accuracy trade-off here? And by and large, what we found is that the group that gets the feedback, which is this red bar line that you see down here, they produce lower forces the entirety of the experiment. So you had 12 trials of this task. The minute they started, and they were trained with the feedback, so they knew what it was, what kind of information it was providing. But the minute we asked them to do the task, they produced significantly lower forces than the control group, and they did it for the entirety of the 12 trials. So then we said, okay, well, if they do really well with forces, what does this mean in terms of the amount of time that it actually takes them to do the task? If they're being very careful and producing less force, maybe they are being slower as well. And in fact, that's what we found. They actually started off very slow. In fact, significantly slower than the control group. But what was interesting is that over the course of the 12 trials, they actually got faster at a faster rate than the control group. And so we think what's happening here is something about the haptic information is actually helping them pay attention to those critical areas in the task where most people get hung up and snag. And once they solve that, they're able to actually do the remainder of the task much faster. Sort of on a different area of the surgical training paradigm, when you look at surgical training, how it's done clinically, there's sort of two choices, right? You can do it either through VR means, which is what happens a lot in the clinical setting, or you can train on the actual physical robot, which is often considered the gold standard. We sort of said, are these two things equivalent, right? Is training in the virtual reality world equivalent to training in the physical world? And this is some work that Guido did when he was visiting my lab, where using the DVRK platform, he basically designed a task that had both physical and digital analogs. And so what you see here is for the same input now, we can actually do the task, and we scaled everything appropriately, so there was no position or geometric scaling here. The exact same task in the virtual world or in the physical world. And then we ran a study where we basically had participants train in one world, real or virtual, and then we had them do a crossover where we looked at their performance in the other world, right? So if you trained on the physical platform, then we asked you to do the task in the virtual platform. Vice versa, if you trained in the virtual world, we had you do the task in the physical platform. You'll see the word sham here because Guido had this really crazy idea that what happens now if you actually do brain stimulation while people are doing the task. So we have a group now that's doing no stimulation and a group that's getting cerebral transcranial direct current stimulation, which has been shown to improve motor learning. And this is in collaboration with a colleague of ours, Pablo Selnick, who's at Hopkins down in physical medicine and rehabilitation. Same paradigm with and without brain stimulation. What we found, and we asked, I should back up, I'm going a little too fast. We asked participants to do the task at 3 different speeds, fast, slow, and then moderate. With moderate sort of represents what is the nominal speed that you would see the task being performed clinically. The task itself was just a needle driving task like I showed you. I will focus in on the moderate case here because this is where we found some of the more interesting results. What we see is that on the left-hand bar plot here, what you see is that we took a baseline measure, asked them to do it about 15 times, looked at their performance, then asked them to train for about 40 trials, and then did an evaluation. Did they get better after training? And by and large, from the red to the green, we got a significant improvement. They got better after training, right? Then we said, now go from the physical platform to the virtual platform. And we looked again at the error metric that they produced. And what we found is that it was no different in the VR world than it was in the inanimate world. They didn't get significantly better. They didn't get significantly worse, right? In terms of the error metric. In the virtual world, that's not the case. They did get significantly better after training. Baseline to evaluation got significantly better, but the minute we asked them to do the exact same task from the VR world into the inanimate world, they actually got significantly worse. The errors went up. So we're sort of saying that there's something unique about the transfer from VR to the real world that we're not fully capturing yet. Now, I don't know exactly what it is. I think a lot of it has to do with sort of the way we render dynamics in the VR world, and how you learn to account for those dynamics, because it's been shown that surgeons learn to account for those dynamics in the real world. VR has its limitations, right? If anybody's ever sat on one of these VR trainers, you know, if you ever hold a suture, the way the suture sort of floats through the air, right? Doesn't act the way a real suture does. Then we said, okay, now what happens when you do the brain stimulation? I'm only showing you the results for the virtual platform because this is where we saw the biggest bang for the buck, is that, remember again, on the left-hand side, I've already showed you this, baseline to evaluation, you get better, but the minute we ask you to transfer from VR to the physical world, you get worse. But that's only the case when you don't have stimulation. When we provided the brain stimulation, what you see is they got better from baseline to evaluation, and then when we asked them to go from VR to the inanimate world, they didn't get better, significantly better, or significantly worse. So we're starting to see results that sort of look like the transfer that happened from the inanimate to the VR world. How all this works, I'll be honest, I'm a mechanical engineer, not a neuroscientist. I don't fully, completely understand, but what we're starting to think of is the cerebellum sort of does this role in sort of helping you pre-plan, right? And it does model pre-planning. And what we think is happening is by doing the stimulation, you sort of overactivate the cerebellum, and it sort of learns this feed-forward model a lot better than when you don't have the stimulation. And so you've got a much richer model when you go in and do the task now, regardless of the environment itself. Okay, last but not least, I'm gonna jump into the fundamental haptic perception work. This is work done by Dr. Singala, who's right here. So we all know, right, that the standard teleoperator, and we want the teleoperator to become transparent, right? You don't notice it, you don't feel it, all you notice is the environment. The reality is, right, transparency is sort of is a theoretical ideal. In fact, we do notice the leader and the follower of most teleoperators, and in fact, most leader teleoperator systems actually add dynamics. And so we begin to ask, what is the impact of these added dynamics to task performance and perception? In order to answer this question, Mohit spent the better part of the COVID era building this setup here that we call the teleoperator testbed. I will describe it to you. You can think of it as a single degree of freedom teleoperator that has an input. It's just an input here, an output here that we can render as both a virtual environment or a real environment. And in between these input and output, we sort of change the transmission dynamics. So we have a rigid rod that connects the two, sort of like the Gert-style mechanical teleoperator. We have two DC motors, which sort of represent your standard telerobotic interface. And then we have this funky mechanical transmission that has both a damper as well as a elastic element in it to sort of render physical spring stiffness and damping. This is sort of what it looks like from a different point of view, so you can sort of see. We sort of did system ID on the system to sort of show that we do in fact get different transfer functions and different dynamics out of it, each of the transmissions. And then we ran this task where Mohit basically asked participants to do an object tracking task, where we did both single sign tracking and sum of sign tracking. We kind of went into this with this sort of, I call it naive now, hypothesis that the transmission that was rigid, remember the one that sort of is just a physical rod connecting input and output, would actually allow for better performance because there's no dynamics really, it's just inertia. And that one of the other two, the electromechanical or the physical system with actual dynamics in it, stiffness and damping, would perform worse. What we actually found, and sort of highlighted here, is that regardless of the transmission, users adapted, right? And this was sort of this, we sort of struggled with this for a while, trying to figure out what to do with this because it wasn't the result we were hoping for, but it's sort of an interesting result still that shows just how robust human control actually is. So much so, in fact, that what we can see in the right-hand side here, when you look, this is just the errors. And what you see is that overall, regardless of the transmission, the users were able to adjust for the dynamics of the transmission to do the task. And the way they did it is, and what we look here, what we call the tracking adjustments here, is what is the over and under compensation on the input side that users had to do in order to get the output to basically perfectly track the object. And what you see is that's where we actually find differences. Based on the teleoperator configuration, these users basically learn the dynamics of the system and can compensate for those system's dynamics in order to do the task. Now, I will say most of these participants only spent maybe 6-7 minutes on each teleoperator before we jumped them into the task. So in that little bit of time, they were able to actually learn the dynamics well enough to be able to compensate for them to do the task. So we're sort of like now figuring out what we do with this result. Maybe we're running some more experiments, but we're also wondering, what happens now when we ask them to sort of perceive the environment? Does perception change in the environment as well? Okay, with the last little bit of time, I will show sort of the most recent work that we've done in the lab. And this totally came, this was all Mohit's idea. And so, it's sort of this out there thing that we'd never really done in the lab before, but is like really interesting, where you all, how many people have heard of the mirror illusion before? Okay, so the mirror illusion, just for those who've never heard it, and I'll show you the video, I can basically have you sit with a mirror in between your body, have your hands located distances apart, and as you start to simultaneously tap and look in the mirror, this phenomenon called proprioceptive drift happens, where you basically start to think of your hand as being equidistant across the mirror as your other hand because you're looking at the reflection, right? So that's this phenomenon. It's called the mirror illusion. It's called proprioceptive drift. They also use it in lower extremity for lower extremity amputees, sort of help with phantom limb pain and things like that. And then there's, of course, the rubber hand illusion, which I'm sure many have heard of, right? Where if you simultaneously stroke your real hand and a rubber hand, over time you learn to quote unquote embody the rubber hand and think of it as your own. Mohit started asking this interesting question, right? If synchronous brushstrokes, in the rubber hand illusion lead to embodiment of the rubber hand, can we flip this paradigm and actually have you embody the reflected hand and make you feel artificial brushstrokes looking through the mirror? And so I'll show you basically better than I can tell you. So we created this setup here. It basically has a servo motor on a linear rail or linear actuator that basically brings a brush in contact with your finger and strokes along the length of your finger, right? And that's what you see here. We have two of these that are spaced equally apart from each other. And what separates them in this little middle trace here is a mirror. It happens to be shrouded right now, but there's a mirror there. And so what we can do, as you can hear and see here, is that we can control sort of the actuation on both sides of the mirror of what's happening on the finger. And what you saw here, and what you should have heard is, what you'll see is that we can either synchronously stroke each finger, we can stroke one finger and tap the other, so it looks like this, or we do nothing, where this one doesn't do anything, right? So stroking, tapping, or nothing. I've gotten, and so we asked participants sort of what did they feel, right? And they would say, generally when the mirror is covered, what they see is, I feel a stroke when you stroke, I feel a tap when you tap, I feel nothing when you don't do anything, right? Then we said, okay, now what happens when we actually introduce the mirror? Sorry, this is sort of the control condition without the mirror. And I'll do this so the Zoom people can hear.
Tap. Stroke. Nothing. Tap. Stroke.
Okay. And then we uncovered the mirror. And this is where things get a little bit interesting. And we asked the same question.
Same instructions again?
Nothing. The light stroke. The light stroke. Light stroke. stroke.
Cool. So as you can see here, what for those that understand, whenever we tap and stroke, and you're looking in the mirror and seeing the stroke, participants always feel a light stroke. I've sat in on this experiment knowing what the illusion is, and I always still feel a light stroke. And so we said, can we quantify this in any way? And basically what we did is we ran an experiment where we actually we normalized every participant's finger length, and we said, tell us the furthest location on the length of your finger where you felt anything. And what we found, by and large, is that when the mirror was covered, so the baseline condition here, everybody basically said the furthest that you went on my finger was right where you tapped. But the minute that we uncovered the mirror and they were looking in the mirror, basically what we found is that everybody picked a location along the length of their finger that was greater than the location where they felt the tap. Now, it wasn't the same for everyone, but it was a sensation somewhere along the length of your finger. And so we think of this sort of as this new kind of illusion paradigm where what we've done is create a visual haptic disconnect, and we've asked participants to sort of solve or resolve this conflict in some way by looking in the mirror and basically making sort of what we call a haptic confirmation by just tapping the base of the finger. It's enough haptic visual information to sort of believe that like I am being stroked. So much so that like we did another experiment where we said, how long does this illusion happen? And we saw this residual effect where the illusion actually persists for some time after we stop doing it, that it eventually tapers off. And so then Mohi got really out there right before he left, like 2 weeks before he left, he sent me this request for this Adafruit cart for all these other parts where he said, I want to see what happens now where I don't actually make contact with the finger at all. And so what he got are these little air thrusters that basically thrust air along the length of the finger instead of actually brushing along the length of the finger. That one didn't pan out so well, but it worked really well for me. So much so that we were sitting there and he was like trying to explain to me how the whole setup works. And I said, okay, well, when do you turn on the illusion? And he said, oh, the illusion's been going, right? Because I swore up and down he was actually moving. And I should back up a little bit, right? Because anybody who thinks, anybody who's thought about this sort of, this is a tough experiment with like a lot of confounds. Mohi spent a lot of time thinking about how do I get rid of these confounds. So you'll notice that when this one taps, it doesn't slide, right? So technically, for any mechanical engineering people, you know that when the motor doesn't slide, you don't have that mechanical transient information of the motor moving up and down. Basically what Mohi did is he put another linear actuator underneath the task platform that moves up and down, that gives off the same mechanical signatures and auditory signatures, right? So we know it didn't have anything to do with the fact that like you were using these other incidental cues to sort of parse what's happening and what's not happening. So where this goes, I'm not 100% sure. We think some of it might be applications in like the VR, AR space, because basically what we're saying now is, and this has been shown sort of in other domains, right? With the the haptic rewalking, or where you can sort of follow a curved space, but if I show you visually that you're going straight, you sort of think that you're going straight, right? Or the haptic retargeting, where I basically make you pick up the same object over and over again, but in the virtual world, it looks like you're moving objects around. The same sort of principle is sort of happening here, we think, in a sense. And so what we're saying is that, everybody's trying to create haptic interfaces for the VR world. What we maybe are arguing is that they don't need to be that complex, right? As long as you sort of give that haptic signature in some way, you can make the vision complex, right? And make the vision rich. And all you need to do is sort of give enough haptic information that I sort of believe it's true, right? And so sort of one of the next experiments that we kind of have in mind is actually trying this out with an AR headset instead of the mirror and see if we get the same results. Okay, with that, I think I hopefully went fast enough. I know I was a little bit slow in areas, but I thank you for your time and for your patience, and I will take whatever questions you have. Oh, and one last plug, I am looking for postdocs, so if anyone is getting ready to finish their PhD, is thinking about doing a postdoc, please don't hesitate to reach out to me. Thank you.
We managed to leave a little bit of time for questions. So any questions from the audience, or if someone is on the Zoom Zoom and wants to let us know if anything pops up in the chat.
I don't have access to the chat.
Great talk. I was wondering with that last experiment, that was like super really cool. And then the sense of like, in Bible, we talk about the hand stroke version of the steel. How much do you guys think that feeling that on this right hand is affecting what you're sensing here? And like, if you were to like make this like fake hand instead, how that could mess with this?
Oh, he had the exact same idea. We actually got lost in thought one day because he was like, yeah, well, what if I replaced the real hand with the rubber hand, and I stroke the rubber hand, and what you see is the rubber hand, but then you feel, and like, we sort of like got lost in where the illusion sort of ended and began. But yeah, I think there's something about the real hand getting stroked. There's an open question. What happens now, like, what if I were to put your hand underneath the table, stroked your hand, and showed the rubber hand being stroked? Would we get the same perception? I'm not 100% sure, but it's a really interesting experiment to run.
Other questions?
Not a hemoglobin concentration. There was one where it actually went down with the intact hand, like the cognitive load seemed to decrease.
Yeah, so I know what you're saying. There was one where, let's see if I can find the slide. This one here. Oh, yeah, right? Where you're saying it sort of went down, right? So yes, it is going down. Technically, statistically, it's not. It's no different than zero. You know, I don't think we have enough data to basically say it actually is easier after, you know, like sort of is what the downward trend would suggest. I think that's sort of a little bit of noise in the measurement, you know, but suffice it to say it was no different than zero.
For this particular experiment, this is the second one, I think it was the first one as well. Have you also considered different haptic feedback stimulations other than vibrotactile, let's say some pressure?
Great question. So yeah, so this is some work that my student Neha did while she was a Fulbright fellow at the Max Planck Institute with Catherine Kuchenberger. Different prosthesis. Oh, I probably won't be able to move it. Different prosthesis here. But what we had is this bellow band, which is exactly that. It's a pneumatic, you know, we basically had a finger that had electrodes over it that sort of told you where you made contact along the length of the finger. We mapped that to this like array of bellows that you wore across your arm. Excuse me, there's the sinus infection, post-sinus infection. But what we found, we thought this was going to do way better than vibration, right? Because it was encoding sort of spatially where you were being touched along the digit. What we did with vibration is it basically sort of mapped both the amplitude, and I'll maybe back up and you'll see it here. You know, you can sort of see the way we encoded all this information in vibration is sort of mapping the amplitude and the frequency and putting it in an enveloping function, right? So a really complicated vibratory signal. We thought, well, the pressure is going to be easier to understand. Turns out that it wasn't. It actually did worse than the vibration. And so I don't know exactly what that means just yet, but we have tried. In fact, one of the first studies that we did in the lab when we came in, so I'm working with Brent, for my PhD, we I was trained as a disciple that force feedback is what you do. It's always force feedback, is always force feedback, is always force feedback. So I came into the lab, and we had this exoskeleton that gave force feedback, right? And our first experiment was actually comparing performance with the prosthesis with force feedback to vibration feedback. And it turns out if you understand and do the mapping, once you learn the mapping, it doesn't matter if you map force to force or if you map force to vibration, we got the same result. So I have slowly over the course of many years now become a convert of vibration. I'm almost scared to tell Brent that sometimes when I go talk to him. But it actually works relatively well. And I'm often very surprised at just how, useful the signal is and how much information you can actually encode in it, and people actually do really well. Now, I'm not saying that there's no role for force feedback. There definitely is, right? But for applications like this, right, cumbersome nature by which we do other types of feedback modalities like force and things like that may not outweigh the benefit of sort of simpler architectures like vibration. But Marcy O'Malley's group has also shown skin stretch, and there are other groups out there that have shown other types of haptic feedback that work really well also. So I think we just sort of stuck with vibration because that seems to work really well, but I imagine this would also work with other types of more cutaneous style displays.
We probably better stop here, but we have a bit of a break in Jeremy's schedule, so if you still have questions for him, I think you can come up and ask him. Let's all thank him for the fantastic job.